When we want to reach extremely large numbers, what would be the best way? Adding one by one, 1, 2, 3, 4, 5, 6, 7, or adding 2 by 2 is better, right? 2, 4, 6, 8, 10, 12. Or by tens would be a bit better. 10, 20, 30, 40, 50, 60, 70. But it's still very slow. And if we multiply, which is nothing more than repeated addition, 2 times 2 equals 4, 4 times 2 equals 8, 8 times 2 equals 16, 32, 64, 128, and so on. That's already better. But we can still grow faster. If instead of multiplying by 2, we multiplied the number by itself. 2 times 2 equals 4, 4 times 4 equals 16, 16 times 16 equals 256, 256 times 256 equals 65,536. When we multiply a number by itself repeatedly, such as 2 times 2 times 2, we call this raising a number to a power. In this example, we have 2 to the third power. Similarly, 2 to the fourth power equals 16, and 2 to the fifth power equals 32. This is better because we don't need to increase the number itself anymore, but rather its power. Let's use 10. 10 to the second power takes us directly to 100. 10 to the third power is 1,000. But let's continue. 10 to the sixth power is already 1 million. Now we've reached something considerably large, right? As large as the importance of your like, leave a like there. 10 to the ninth power equals 1 billion. 10 to the 12th power equals 1 trillion. 10 to the 15th power equals 1 quadrillion. 10 to the 18th power equals 1 quintillion. And we continue. 10 to the 20th, 10 to the 30th, 10 to the 50th, 10 to the 60th, 10 to the 70th, 10 to the 80th, which is the number of atoms in the observable universe. And that alone is already an absurdly large number, but mathematics doesn't care, and neither do I. So let's increase more. 10 to the 100th power, which equals 1 followed by 100 zeros, is called a googol. 10 to the 100th power equals 1 googol. The term googol was coined by mathematician Edward Kastner's 9-year-old nephew in 1938. And yes, this is indeed why Google chose its name, to represent the vast scope of information on the internet. But what if we raised 10 to a googol? That would equal 10 raised to the power of 10 to the 100th power. This would give us the absurd googolplex, 1 followed by a googol of zeros. And that would be 1 followed by, wow, that's crazy. This already escapes our comprehension, escapes human understanding. If all the matter in the universe were transformed into paper and pen, there still wouldn't be enough material to write this thing down. Very good. Awesome. But all these powers of 10 will eventually get tangled up. We need a way to make even bigger jumps and grow much more. But how? We've already gone through addition, already gone through multiplication, which is repetition of addition, already gone through exponentiation, which is repetition of multiplication. So would it be possible for something to exist after exponentiation? Tetration, which is nothing more than repetition of exponentiation. Look, 2 tetrated to 3. Since it's repetition of exponentiation, it would equal 2 to the power of 2 to the power of 2. 2 tetrated to 3 is nothing more than a tower of exponentiation that repeats 2 3 times. And then we do the exponentiation the way we know. 2 to the power of 2 equals 4, and then it becomes 2 to the power of 4 equals 16. The most common notation for this is up arrows, right? For example, 2 tetrated to 3 equals 2 double up arrow 3. Imagine then that you're thinking if something could exist beyond this. And yes, exactly. Exponentiation equals 1 up arrow. Tetration equals 2 up arrows. And after it comes pentation, which is repetition of tetration. Then comes hexation, which is repetition of pentation. Then comes septation, which is repetition of hexation. And octation, which is repetition of septation. And so on, going on to infinity and beyond. All of these are called hyperoperations. The next hyperoperation after tetration is pentation. For example, 2 pentation 3 can be written like this. It's the repetition of tetration. So 2 pentation 3 equals 2 tetration, 2 tetration 2. The alternative notation for pentation is the exponent below and to the left. So 2 pentation 3 would equal 2. Tetration 2 tetration 2, which would equal 2 tetration 4, which in turn would be 2 to the power of 2 to the power of 2 to the power of 2. And doing the calculation, we see that 2 to the power of 2 equals 4, 2 to the power of 4 equals 16, and we get 2 to the power of 16 equals 65,536. So see that 2 pentation 3 is the same as 2 to the power of 16. So how would hexation work? 2 hexation 3. Look, by the arrow notation, 2 hexation 3 equals 2, pentation 2, pentation 2. This becomes 2 pentation 2, which equals 2, tetration 2, tetration 2. This equals 2 pentation 2, which equals that 2 tetration 2, which equals 2 to the power of 2 equals 4. I think I didn't get confused and spoke correctly. I don't know, I'm already lost in the notation. In the alternative notation, the exponent goes below and to the right. I think this one's cooler. So 2 hexation 3 will equal 2. Pentation 2 pentation 2. See, hexation is determining that 2 will repeat 3 times. And this will be what? 2 pentation 2 equals 4. So it becomes 2 pentation 4. So 4 now determines the repetition of tetration. So see that it becomes 2 tetration, 2 tetration, 2 tetration 2, 4 times. So we do this calculation. 2 tetration 2 equals 4. We already saw that 4 tetration 2 equals 2 to the power of 16. And 2 to the power of 16 equals 65,536. So this would become 2 tetration 65,536. That is, we would have to make a tower of 2 to the power of 2 to the power of 2, repeating the number 2 exactly 65,536 times. This would give an absurdly large number that I don't even know what number it is. Son, that's crazy. So now let's stop playing around with 2 and see what happens if we change the base from 2 to 3. Let's see how much difference it makes. 3 cubed. This is easy for everyone, right? It's 3 multiplied by itself 3 times. 3 times 3 times 3 equals 27. 3 tetration 3 will equal 3 to the power of 3 to the power of 3, which will equal 3 to the power of 27. This, my friend, gives 7,625,597,484,987. So how will the pentation of this work? 3 pentation 3. That is 3 tetration 3, tetration 3. And we just saw that 3 tetration 3 equals 7,625,597,484,987. So 3 tetration 3, tetration 3 will become 3 tetration 7,625,597,484,987. This means we would have an immense tower of 3 to the power of 3 to the power of 3, repeating 7 trillion times. Son, that's crazy. What has limits our municipality? Mathematics doesn't. And now just one more interesting curiosity. Regardless of which hyperoperation we use for 2, it will be indifferent. See, 2 is an interesting case. 2 times 2 is always equal to 4. 2 to the power of 2 will be 2 times 2, which equals 4. 2 tetration 2 will equal 2 to the power of 2, which equals 2 times 2, which equals 4. 2 pentation 2 will equal 2 tetration 2, which equals 2 to the power of 2, which equals 2 times 2, which equals 4. 2. Hexation 2 will equal 2. Pentation 2, which equals 2. Tetration 2, which equals 2 to the power of 2, which equals 2 times 2, which equals 4. The number 2 is hacked. Nothing works with 2.